As you know, our speaker tonight is Tim Pinkney, NASA ambassador. And without further ado, I'll get out of the way and let the star of the show take over.
Well, I've started my timers, so I won't run too long. And good evening to all of you. Thank you for that brief, wonderful introduction so that we can spend more time on this fantastic machine called the Webb Space Telescope. This is my 100th presentation that I've made within the last 5 years. So it's nice to be a Centurion NASA advisor, and glad you're all here, all 41 of you so far. And let's, got a lot to cover, so, and your time is finite. So as we used to say on board the aircraft carriers, launch them. So let me get to my screen here. There we are. You all see that? I assume so. Otherwise, someone interrupt and say hello.
We can see it, Tim. We can see it.
Okay, super. Thank you very much. The 1950s and 60s are often referred to as the golden age of space exploration. It's a time when humanity took its first steps from Earth out into the stars. And today, 70 years later, we're living at the dawning of a new golden age of space exploration, with missions launching at a rapid rate from many countries. You may know that India put an orbiter around Mars last year. China is exploring the far side of the moon. Additionally, we're posed on the Artemis program to return to the moon, and we've got robotic missions that are taking us deeper into the cosmos every day. So today's topics, the James Webb Space Telescope, is probably the most indicative example of a mission that will change, alter, and discover what we know about galaxies, nebulae, and exoplanets that is different than we know now, and that we may even find life when we have a better telescope. You know, the noted astronomer and author Carl Sagan said, "Telescopes are time machines." And James Webb is the largest, most powerful, most complex, most complicated, and as you might have guessed, also the most expensive spacecraft ever launched into space. That is the Space Telescope. But I firmly believe we're going to get our money's worth. It fundamentally will change the understanding of the universe. And so as soon as I get my slide to move, as mentioned, I am a solar system ambassador, and there's over 1,000 of us in the United States. If someone wants to ask a question on how to become one, let's do that during the Q&A. Also, as ambassadors, we don't represent NASA or Jet Propulsion Laboratory. Comments, questions, and smart aleck comments are all mine. Also, before I leave the solar system, many of you may know that NASA includes people's names on their spacecraft landing on Mars. And you can do that by simply Googling Mars, send name to Mars. And already there are 21 million people whose names are going to go on the next spacecraft, which we don't know when or what it will be. But I can tell you, I'm on 3 of them already. The InSight, Curiosity, and the Perseverance rovers are got my name on them, and I'm very proud to have them there. I also get frequent flyer miles, so I've just passed 1 billion frequent flyer miles for NASA. No free tickets, but at least I got that distinction. The Webb Telescope is a time machine that's going to take us back to the Big Bang, and it's going to take us back within 200 million years, which seems like a pretty good length of time since the dinosaurs died 65 million years ago. But 200 million years ago, after the 200 million years after the Big Bang, is how far Webb is going to look back and show us things that we have never seen. And basically, it's going to be looking back in time 98% of the time since the Big Bang. That's what we're all excited about. So we're going back to the Big Bang, almost. So let's take a closer look. The machine was launched, spacecraft was launched Christmas Day, and it's going to be telling us a lot of things. And what I'm sharing tonight is about the man, Webb, the mission, and the machine. And also, but before I do that, I want to give you a quick background about the electromagnetic spectrum, because if you don't know that, then you'll get lost before we go any further. And basically, all forms of light are some form of electromagnetic energy. And here are 7 of them. We're familiar with the left-hand side, at least with X-rays. Most of us have had that in our lives. Ultraviolet, anytime you get a tan, that's the sun throwing off ultraviolet. Visible is what we see with our eyes. And on the other side, infrared, we often keep our food warm with that. We all use microwaves and listen to radios. So radio waves have a way of also being used for exploration. One of the things that we'll be talking about a few minutes down the road here is that light from galaxies and stars first shine in the ultraviolet spectrum. And then over time, they get stretched out to infrared. And infrared is what Webb focuses on. And so that's why the gigantic mirror is going to be focusing on infrared, so that we can see this stretched out light from years and years and billions of years ago. Here's an electromagnetic spectrum of the Milky Way. And what you see there on the left is what it looks like an X-ray, then ultraviolet. Hubble shows you what visible is. And this is Hubble with infrared, but what we're going to see with the Webb and also radio. You can see it's all the same galaxy, but it's all different aspects of it that we see because of the different light that we use to investigate. We're all familiar with the rainbow. Each of our visible colors are well known to us. We see that every time there's rain and sunshine and the light is correct. But infrared is invisible to our eye. A couple of animals can see that, but we can't. And it was discovered a little over 200 years ago. And since that, we've been building warmers and our TV controllers to make sure that we keep up with technology. But what we're going to focus on the rest of the presentation is the infrared. And let's look at that. Visible light looks like this, but if you were to put it in a photograph it in infrared, it would look like that. It would be the heat generated, and mercats have a lot more energy than a cold crocodile. So pretty interesting how that all just can change. And so in the electromagnetic spectrum, we've got the visible above there, which we see. On the left-hand side, Hubble focuses primarily on the visible, but with a few additions and repairs that it had, upgrades, it got into the UV. But Webb is going to be focusing on the infrared. And we discovered the infrared with the guy named Edwin Hubble. I shouldn't say the guy, he was a scientist and astronomer. And before him in the 1920s, we thought the Milky Way galaxy was the only galaxy in existence. And kind of short-sighted on our part, but it wouldn't be the first time in human history that we thought we were the center of the universe. But what he is most noted for in what this discussion is all about is that galaxies red shift because the universe is expanding constantly and accelerating as it goes along. So light stretches, and we call that a cosmological redshift of the ever-expanding universe. And so here's a graph. You have the galaxies on the right-hand side, and they're sending out powerful ultraviolet light. But as the universe expands, the redshift occurs and changes colors and finally goes down to infrared. And that's how we now see great distances. Oh, infrared will also have some other advantages, but I thought an interesting fact that not everybody knows, that during the 90 minutes we're going to be talking tonight between the introduction and Q&A, the universe will have expanded in all areas 235,000 miles. That's about the distance to the moon. And in 24 hours, the universe expands 10 million miles further, which is about 400 times around the Earth if you were trying to measure that. Just in a month, 300 million, in a year, 3.6 billion miles. And during the 20-year life of Webb, expected to expand another 72 billion miles away. So those numbers are somewhat boggling to me. And the fact that it's been doing this for billions and billions of years, quite amazing. One of the challenges, though, of visible telescopes, the ones that we use primarily here on Earth, is dust and gas and just junk that is floating around up in space. And so the way we can fix that, that is see through it, is to use infrared cameras and spectroscopy, which we will talk about later. Webb has both near and, more importantly, mid-infrared. Mid allows us to see even farther back. And so here's an example that we used at the Aerospace Museum of visible light. And then when you put it in infrared light, the black bag disappears, the dust disappears. So you can see right through it. And that's the whole reason that Webb is designed for the infrared. We all know what a stove looks like when it's turned off, but it still has heat. Of course, when it's on, we can see it's red, but it's infrared because it still has heat. You can see it glow and then really glow when the heat is really hot. So that's the reason we, again, use infrared. And we get to feel infrared anytime we go out in the sun. Like today, your skin gets warm, and that's actually the infrared letting you know that it's feeling or seeing the light of infrared light. So here's the visible light image again. And when you do the infrared, you can see all the blue gas is primarily gone in the background. And look at those thousands and thousands of stars. Most of the dust has disappeared in the pillars there. And if you were to look at this with the mid-infrared, this is what you would see. Now, unfortunately, Spitzer had a very small mirror, and the clarity of pictures depends on the size of the mirror. And so I'm going to show you, that's why it's not very well in focus. But if you look at the mirrors here, Spitzer was only just under 3 feet wide, whereas Hubble is 7 feet and Webb is over 21 feet wide. So we're going to get some pretty impressive pictures. It's 6 times larger, and interesting that Webb, even though it's that much bigger, is actually 200 pounds lighter than Hubble, because it was made out of beryllium metal, and gold is a wonderful reflector of infrared energies. So it's treated with a thin coat of gold, which is why it's so yellow. And thought we would have some fun here. Most of you probably know what the official name of our star, our sun, what it really is called. And if you if we were doing this in person, I'd have you all raise your hands, but there's the answer. It's the Sol, or its Sol. And likewise, what is our moon called officially? Not our moon, but going once, going twice, Luna. And so there are lots of moons in the solar system, so we can't just call it the moon because there are over 200 named moons in our solar system. So let's talk briefly about the man. James E. Webb was the second administrator of NASA. He basically was responsible for the Mercury, Gemini, and Apollo missions. He predicted 60 years ago the need for a large space telescope, and probably the reason that he got that name. He is the only bureaucrat, the only non-scientist to have a name affiliated with a spacecraft. And want to reiterate that Webb is not a replacement for Hubble. Hubble's got another 10-year extension, so it's going to be looking good for a while. And where Hubble uses visible light, as I said, infrared. So let's go back to the solar system and say, is there a solar system moon out of that 200 that have an active volcanoes and actual lava flowing? True or false? The answer is, if I've got pictures of it, it must be true. And that's the moon Io. And so it has over 400 volcanoes. It is the most active volcano entity in our solar system. And what's the average distance between the Earth and the moon? You all probably know this, and that is just about 250,000 miles. You may not know that Saturn's rings are just about 250,000 miles from one edge to the other. And Saturn is basically 8 Earths wide. Let's make that 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 Earths wide. Sorry about that. And it would take 1,300 Earths to fill Saturn. That's how big it is. And if Saturn was as close as the moon is, that's what it looked like when you're driving down the road. So just get your cameras out in case that comes a little bit closer. Wanted to show the difference between some visible light and infrared, and the Orion Nebula M42 and 43. Pretty impressive. You can see a lot more stars, less gas, and Webb is going to be even more. All the pictures that I show you today will be from Hubble or Spitzer or another spacecraft that have some infrared capabilities. They won't be nearly as great as Webb is going to be. So let's focus on the mission now, and that's going to be literally to go where no telescope's gone before. Here's what we think Webb simulated will look like as compared to Hubble. Far more clarity, many more objects, certainly far, far deeper. There's 4 main focuses that Webb is going to have, and that is the early universe. And to that, what were the first stars like? We don't have an idea at all. We really don't know. So we hope that Webb will help us with that. Here's how Webb is looking back. We're currently at 13.7 billion years, and we think we'll be going back to 13.5 years from now, just a few 100 million years from the Big Bang. We hope to see the first stars, maybe, and certainly the first galaxies. This is explaining the same thing. This is from the Hubble Extreme Deep View. But recently, I don't know if you caught it, but Hubble broke its own record. It used to be just 4 billion years away is the best what Hubble could see. And it caught a lensing experience. So it was looking back at about 1/3 of the current age of our solar system. And then because of lens curving, this star showed up, and it was named Arundel, which means morning star in Old English. And it was this ripple in space-time that provided the extreme magnification. And it's got us within 7% of the Big Bang at redshift for you scientists, 6.2. And finally, here's a close-up giving some points. There's the star over there on the right-hand side. Between it are mirror star clusters. Those are actually the same star cluster, but repeated because of the lens distortion by gravity. This magnification line is what happens when you go around a mirrored system. And it's as though you're looking through an extreme edge of a magnifying glass. The other side of that is warped, but it's also magnified. And that's what we're seeing. And this is the line that is that appearance. So anything on that line is significantly magnified. So that's within 1 week, we just found this out. Pretty impressive. And there's the actual blob star. We think that's a single star, not a group of stars. And everyone's waiting for Webb to confirm if this is an early star has only helium and hydrogen, not metal in it. So it'll be very significant if it discovers a legendary population 3 star, which is a massive metal poor star. So stay tuned on that. We are looking back into the oldest galaxies, and Hubble's ultra deep field took 16 days to take this picture. And because of the size of Webb's lens, it can do the same thing in 7 hours. Pretty amazing. So we're going to be seeing a lot of what's going on, which at the star's life cycle. And here's again another picture of a nebula and how getting rid of the gas and dust, or a great majority of it, will have infrared light. Again, this is not a Webb photo, and when it is, it will be much clearer. The pillars of creation have always been a favorite popular photo, and I didn't realize it was such a small portion of the giant Eagle Nebula. And here it is again there inside the nebula. And when you blow it up, you get that famous, gorgeous, spectacular photo. And as I was doing some more research on this, you kind of get lost on the size of galactic entities. Just this pillar alone is 4 light years tall. That's 24 trillion miles just for that arm of that. And it's 30 trillion miles wide. Just unbelievable distances. I think if you were inside one of that, you would not see the dust or the stars. It would look like you're just looking at our own light. And if some of you have a different opinion of that, I'd sure love to know it. Spreading out a 24 trillion miles for that gas cloud. So we're going to be looking at star life cycles, and then we're also going to be looking at other worlds, our own solar system, as well as exoplanets, planets that are being discovered around other suns, around other stars. And here's one that is anticipated what it would look like from Spitzer telescope versus Webb's mid-infrared imaging system. Here are the current, well, not totally, but 4,000 confirmed exoplanets. And with so much more ability to see how many more exoplanets are we going to find. In the green box, there are 53 of them that are potentially habitable. They may have water on them, and the warm Terrans would have water on them, and the super Terrans are bigger Earths that would have water on them. So stay tuned. We'll find out more later on that. You all know that the Earth is in the Goldilocks zone, with the two first rocks being too hot. Mars and the gas and ice giants are too cold. And of course, Earth is just the right distance from our star. Well, we found a system, and you probably have heard of it, the TRAPPIST system, where you can see Earth there in the blue. TRAPPIST has its planets, its planets, Delta and Echo, D and E, that are also in the habitable zone as near as we can tell. This system is not as big as our solar system. Their star is not as big, but it's something that has been the most studied solar system, and it's only 40 light years away. I mean, just a mere 240, let me do this right, 40 light years, 240 trillion miles away. Piece of cake to get there. Last month, we've got pictures of planets that have formed, but we haven't been able to see actual formations of planets and moon disks. But last month, one of our spacecraft caught this picture, and you can bet that Webb is going to take a much closer look at it and see it in greater detail. But until then, we're pretty excited that we've got to see something that's actually forming a solar system. And before we leave this topic, let's plunge into which of our planets has the largest volcano on it. It's the second smallest planet in our solar system. That's Mars. It also has the deepest, longest canyon in our solar system. We'll be re-examining what our solar system looks like. This is what Hubble has shown us, and this is a simulation of what Webb will be seeing. And so it will give us a much different view of and understanding about that planet. I've already given you the answer to this particular question. Here's Luna. It's the 5th largest in our solar system, but there are 4 other moons that are larger. And together we have over 200 of them, all with names. So that's why we call it Luna. And this is a relatively new update, but how many moons actually have liquid water, or we believe liquid water, under the surface ice? That's a pretty amazing number also. These are all about 1 billion or more miles away from the sun. So it's pretty quizzical as to why there's liquid water under an ice core or an ice coating. And it may be that there's rocks. Some of them have gravitational interactions, like those moons that are orbiting Jupiter that are tugged. The Jupiter moon Io, which I'm trying to see there, that has the volcanoes, moves as much as 30 feet a day as it circles the Jupiter. It's just like our tides. It comes and goes based on the gravity. So that push and pull keeps liquid water available on these various moons. Out of the 200 moons, there are only 1 moon with an atmosphere. That's the moon Titan. And here's a cross-section taken by the Cassini spacecraft as it went down through the atmosphere to land on that moon. It was paired up with Cassini, which studied Saturn for over 13 years. So this is a pretty impressive picture. This could be Earth in its different layers of the atmosphere. And because it has an atmosphere, NASA has created a drone that will fly on the moon called Dragonfly. and it plans to launch later this decade. Takes 7 years to get there, and it plans to be working for 3 years. I hope to look forward to see that landing. It's much like Mars's Ingenuity helicopter. Well, in the fact that it's a helicopter, but it's much different because Titan is so far away. So it's inspired by Ingenuity, and it weighs 900 pounds. It's a pickup size of a small pickup. It has 8 blades in sections of 2, mounted just like Ingenuity has. And then being 1 billion miles from the sun, it can't rely on solar panels like the Ingenuity does. So it has to be nuclear powered. So a nuclear powered 900-pound drone will be flying towards its rocket, will be flying towards Jupiter later this century, later this decade. And I never want to forget about our own moon. You all know about Mount Rushmore, and probably most of us have been to it, but I'm always curious and I want to see what the backside is. And so I took a picture of the backside of Mount Rushmore. And what I discovered was 4 more moons. I hope you're laughing back there. I can't hear you. Okay, so we move on now to, I remind you that these are my opinions, NASA, not NASA's or JPL. Another pretty picture of Hubble and infrared will be showing. And I wanted, there's no sound on this, but I thought it was pretty and kind of curious to get an up close and personal view. So let's see what we can do here. You can see the gases being blown off from this as they feather out into the surrounding space. Again, I'm just blown away with how many stars are out there that are hidden behind all the gas and debris that are around various nebula. So let's look to now the machine. The Webb telescope was designed and redesigned for 9 years, and then it took 11 years to build. And for the last 5 years, all that's been done is just being tested. Just a component, and then a subassembly, and then assembly into the whole telescope. It was originally budgeted for a mere $500 million. And it's coming in currently just under 10 billion, but I think we're going to get our money's worth. It's going to be impressive. It was originally planned for 10 years, but the European Space Agency rocket Ariane 5 put it in such a wonderful optimum trajectory that we think we'll be able to get, it didn't have to use its own fuel. So it's probably going to get a 20-year mission, or somewhere between 10 and 20 years. So that'll be great as we are looking down the road. Now, Hubble is pretty good size, being the size of a bus, but Webb is the size of a tennis court. And so it's, here's a life-size replica of it with humans standing alongside to give you some idea just how big it is. And as you know, size is important, and it's 3 times as wide and can see objects 9 times more faint than Hubble. This is another projection of what Hubble would see looking at far, far away, and what Webb is going to be able to see down the road. So stay tuned on all of that. I mentioned that the yellow is based on gold-plated beryllium, and each segment of the gold and its backing weighs 45 pounds, and then another 45 pounds of mounting. So each of those segments is 90 pounds. But here's something that's just amazing about this gold. It's the weight of a golf ball. And the weight of a golf ball in gold, because it's so dense, is actually the size of a marble. And so a size of a small marble is what coats the entire 18 segments. And they do it because the gold is only 1/10,000th of a human hair thick. Remarkable technology to come up with that. But gold is the best refractory of infrared light, so that's why it was used. There are 2 sides to Webb. The side that faces the sun, and that's called the hot side, pretty obvious. And then there's the cold side. And that's where we want to have all the optics, because we want them cold as possible. The big kite that you see is really 5 layers of 1 millimeter thick aluminum foil, for lack of a better word, that's been coated and treated. And you can see here that the outer temperature is somewhere in the minus 390 degrees Fahrenheit. And at the very bottom, that's minus 390. And the outer layer, where it first hits the sun, is 260 degrees Fahrenheit. That's over a 600 degree difference in 6 feet. Each of those sheets is slightly larger. Well, let's put it this way, it's slightly smaller that's above each one. So the heat can escape out the sides and front and passively cool the apparatus. And so you've got 260 and 390 here. And if you are into Celsius and European measurements, those are the temperatures there. My last presentation was to Europe, and so I had to convert a lot of this for them. Here's the 5 layers, so you can see each section, and combined, they create enough sun blocking to be the equivalent of an SPF of 1 million. So the cold side, the light comes in like this. It bounces off to the secondary mirror, the primary mirror being all gold, and the secondary mirror focuses it in to the inside to actually a third mirror, which then reflects all over the place for all of the various apparatus. So the Canadians provided the fine steering mirror, which is what keeps Webb on track. It focuses on a single star for steering, while the camera itself and the primary lens is focused on other areas. There's all the size of the mirrors that are involved, and impressive technology. So remember this picture, we had visible light and infrared, but we also need spectroscopy. And what is spectroscopy? It is dividing light up and filtering it through a metal plate that bounces off a certain kind of grating that then splits the light like a prism, like a rainbow, just like we see when it goes through a piece of triangle glass. And then the spectrum picks that up. And every element has a unique spectral formula. So we can tell the velocity of gas and the density, we can tell temperature, and the speed of stars. We can tell the composition of atmosphere and the minerals that are on the planet, all through spectroscopy. Pretty amazing. Here's a simulated what Webb can do, but based on the wavelength, and water is different than methanol and different than carbon dioxide. Well, we all know that from our high school chemistry, but it also they have different spectrums, and that can be readily apparent and easily detectable by Webb. Here's the 4 instruments, and it basically breaks down to 3 different kinds of things. And what I'm going to do here is, this is a 30,000-foot view. This is big picture. All the instruments have a camera. All the instruments have a spectrograph, which breaks the colors down and therefore the elements. And most of them have, 3 of the 4 have chronographs, which basically is a black thumb in front of light. So it blocks the starlight so you can see planets that may be nearby. It darkens the bright spot. And so those are the 4 instruments, and that's all that there is. But as I go from 30,000 feet down to 20,000 feet, it's telling you a little bit more that there are standard cameras that would be like you and I taking a digital camera, and there are chronographs which block out the sun. There's interferometry photography that blocks bright objects, so that when they're too close together, we can block them out, basically like putting your thumb in front of a camera. And then it's got a time lapse. So it can look the difference between a star's brightness or the motion of planets as they go around their star. Now, as I come down to 10,000 feet, I'm looking a little bit more carefully at the different kinds of capabilities, from wide field to single object to split, and the ability to take multiple objects all at once, and then integral big picture of entire galaxies. And then again, the time lapse that we just talked about, all pretty capable. This is what the spectroscopy would look like as it comes in to this into Webb and Webb's instruments, and you'd be able to tell very easily the fingerprints of oxygen or nitrogen or sodium. They're all different. So that will be a huge, I've always wondered how do they know that there's carbon monoxide on that planet? Well, this is the way they do it, through spectrography. And so here's what it would look like if you were getting the basic planets themselves and the gases that they have as it comes off as big picture. Earth is much different than the ice giant Neptune, which is different than the gas giant Jupiter. So you can see the difference there. And the NASA folks can tell you what that spectrography can do, the surface temperature to how fast it rotates, and what the atmosphere is composed of, in this case, mostly hydrogen. So remarkable amount of information just from being able to break down light. So as we get down to 5,000 feet, we're looking at the 4 different instruments here, and I will talk about each one of them. The one that can see the farthest is the mid-infrared instrument. The other 3 in the near infrared, that's what NIR stands for, near infrared spectrography, near infrared slitless spectrography, and the near cam, which is a camera. So let's go in a little bit closer on that. Now we're looking at the mid-infrared. It's got a camera, spectrograph, chronographs, and the ability to integrate lots of pictures. You can see at the bottom, there is it's in the mid-infrared section. And this is built by the European Space Association, the European Space Agency, ESA, and along with JPL that helped some of that. And this will be giving us some truly truly spectacular astrophotography. There are 4 capabilities in this, and this is more for the scientists in the group who understand what these images mean, and sorry, not what the images mean, but what the definition and the areas that it covers. So I give you a moment to look at that because I can't explain it, but I wanted you all to see it. And if you really like it, take a screenshot. I have sources that I cite at the end, so you don't have to take this particular one, but there is a site for the general public, and then there's a site for scientists. This comes from the scientist's point of view. So does this, telling you more about the mid-infrared. This is from the Pocket Handbook, and give you a second just to look at that and say, you fully understand it, you partially understand it, or it means nothing to you. This hasn't not been updated since 2014 because all the instruments were locked in and figured out how they were going to operate. So there's more available at the websites that I'll tell you later on. I thought this was interesting in that the near infrared camera shows you the picture there in the center. But if you want to look at a first light, that is one of those first stars that we're trying to see, you need the mid-infrared. And you can see that orange line going down, which is increasing the capabilities and the ability to see those distant objects. All of the space instruments, except one, are perfect in space. Space is not totally ice cold. Ice cold, as in no movement of atoms, is called 0 degrees Kelvin. And so Kelvin doesn't measure heat, it measures cold. And Kelvin, 0 Kelvin is 495 on the Fahrenheit, or minus 495, and minus 273 on the centigrade, just to give you some base of what we're talking about now. So the primary mirror is kept at about 50 Kelvin by just being in space. And the instruments, because of the way they were placed, 3 of them, they're at about 40 Kelvin. But the mid-infrared range has to be below 7 Kelvin. And you can't get there from here just being out in space. You have to have a cooler. And so MIRI brought along its own cryo cooler to bring it down another 30, almost 8 degrees from 40 Kelvin down to 6 Kelvin. And I'll do the math right, try that, 32 degrees Kelvin. And so Webb's capability for the distance will be for the mid-infrared range distance will be dependent on how long this cryo cooler works. And unlike a ice box or an ice chest that you might take to the beach that puts ice cubes in it that eventually melt and therefore your drinks get cold or get warm from being cold, MIRI is much like an ice box, like a refrigerator. It's plugged in, it gets electricity, and it just keeps pumping. It'll only stop cooling when the parts wear out, which is not expected for at least 10 years. So that's going to be the controlling factor of that. Here's the timeline of the launch, starting way up on the left-hand side, and the cooling process. You can see how quickly the 3 at the bottom cooled, 3 instruments, but the MIRI took a very, very long time over there on the right-hand side when it finally crossed down to 7 degrees. And that happened last night. So everything on Webb is now ready to start operating. All the instruments are cool. Now they have to still align the mirror in what's called phase 7 of the mirror alignment, but we're getting really close, folks. The other instruments, the near-infrared spectrograph has spectrography, and an amazing thing, the micro shutter array, as well as an integral field. It's back in the near infrared area. But you know, the iPhone has 4 cameras on it, and it looks like Webb has 4 cameras on it too. Here's the lenses for those 4 cameras. But that's not the case. The reality is that each of those squares is 62,000 shutters. Right there, 62,000 times 4 gives you almost 250,000 shutters. And amazingly, 100,000 of them can be open at once. This is kind of what it looks like when the shutters are open. Looks like little specks of dirt, but they're actually the shutters. There's a close-up of the shutters and even a bigger close-up. The width of each shutter is about that of a human hair. So again, and it's run electromagnetically. It's a magnet that switches on, switches off, opens up, closes. Remarkable. Here's an illustration of what it can do. And so the whole point is, if you've got 10,000 stars out there and you're interested in 100 of them, just open up that one slit that's for that particular lens. And so it can literally take 100 pictures at a time. You can study 100 lights, universes, galaxies, whatever, at a time. Hubble can do 1. Amazing. The NearCam also has 2 cameras that are identical, one that's short wave and one that's long wave. And they also are remarkable cameras. And the whole idea is the Webb is 1 million miles away from Earth, and it can never have a rescue mission. You know, we sent 5 rescue missions to Hubble, but it can't. So there's duplications on every single thing that Hubble has, every instrument. And this is a case where module A and B are just duplicates of each other. And the last one is the camera that also has the different mask and spectrographs. And so the picture here is just giving you a little bit of excitement about what Webb is going to be able to see. Again, these are actual pictures from other cameras, not from Webb. Webb's going to just blow our socks off again. So on December 25th, the telescope launched and headed out. First of all, it launched from French Guiana. And why there? Because the equator's there and the Earth spins faster there. And that's why we have Cape Canaveral or Cape Kennedy as far south as we can go in the United States. That's the reason why, is because it gets added energy as it takes off. And Webb was constructed finally in Los Angeles and sent from the port of Long Beach on a ship that carried only Webb through the Panama Canal, got down to the French Guiana, and then launched. And just a couple hundred seconds after liftoff, it shedded its air nose cone, and at 75 miles high, blew them away. And the spacecraft basically took off on its own. That's the last picture of Webb we will ever see, at least of the spacecraft. But an astrophotographer did take a picture. He was working on another exposure, and Webb photobombed the camera there with a white streak going across. Pretty cool picture along the way. Webb headed out to Lagrange point 2, which is a point that every 2 gravitationally interactive entities have. So this is just the sun and the moon with the Earth in there, the Lagrange 2. And if you want to make sure NASA did it correctly, here's the calculation that you can use take a Photoshop and or take a screenshot and check out the math on that. What I like about this is Einstein told us space and gravity warp. Space warps because of gravity, and here you can see the sun sinking gravity pretty heavily, and the Earth and the different Lagrange points that are there. This happens, as I said, on any two bodies. And Webb is solar powered, so it must always be in the sun and never in the shadow. So Lagrange point 2 is actually in the shadow, and the L2 orbit is actually larger than the moon's orbit. Here's a different picture of it going around L2, and NASA is smart enough to figure out that there's radiation pressure because of the sun taking those sails and trying to blow them away, and also the gravitational force of the planet and the sun. So it's been compensated for that. And every 3 weeks, there's small rocket engines that will keep firing Webb to keep it looping in a halo orbit. This is the only fuel it needs, and that's when that fuel runs out, then basically Webb is no longer controllable and no longer functionable. But we expect that to last somewhere between 10 and 20 years. So at the L2 orbit now, for the last month and a half, it's been aligning its mirrors, 18 mirrors that aim every way that they want to aim. But NASA picked out a star that was far away with a fancy name of HD 84406. And it did it because it was primarily not around any other significant stars. And each of these has to be tilted to align their spots. So it's just like when you work on your own car and you are backing out, you want to make sure your mirrors are adjusted. Each mirror has an adjustment, 7 ways to bend. There's 2 on each of the 3 extensions there and 1 in the center. You may recall that when Hubble got out, it had 2 micro something or another warp in the mirror. And so we had to send up a repair to get optical repair. Well, this way we don't have a capability of tweaking it. So we built in a tweaking capabilities, and these will be tweaked at least every 20 days to make sure that they're all aligned, all 18 mirrors. So the very first selfie of the 18 mirrors, 1 was aligned, and that's the white one. And still took a month before all the other ones are getting close to a star. Here's the way it looked originally, the different wings, as well as kind of just the way the mirrors got rattled on the launch. But this is the way you wanted to get it to look. It kind of matches up this way, and then you get it further into a better focus. And using this star, this was the best picture that we ever had of it. And Webb's very first picture of that star was like this. And that just made everyone so excited. You can see solar systems behind there, or you can see galaxies rather behind there. And after tweaking the mirrors a little bit more, this is the image now. The streaks are fewer and fewer. And I also put out a reminder here that Webb is so sensitive to heat, it never can look towards the sun or Mercury or Venus or Earth, anything, or moon, towards the sun. But outside of that, focusing away can take pictures of Mars, all the solar system, and the rest of the universe. So as of last night, the spacecraft temperatures were looking good on the cold side. We remember we want 390, and so on the cold side, that was just fine. On the hot side, those were actually a little lower than expected. That was good. But the most important were the instruments. And here, all 5 of the instruments, the 4 that we look at, that we've been talking about, as well as the steering mirror, are all as cold as they need to be. The very first one, you can see it's 6 degrees Kelvin. and all the other ones needed to be below 40 Kelvin. So we're in great shape that way. And so what's next? Well, now that the temperatures are all correct, there will be fine tuning of each instrument with each of the mirrors, with the 18 mirrors, to make sure that those are all finally set up. Then it's going to take pictures of known capabilities. That is, pictures of, to test the capabilities with known star pictures. And then sometime in June or July, we're going to have photos released to us, and scientific exploration will follow shortly thereafter. And here's what the first 13 early release programs, 4 of them focused on galaxies, a couple of massive holes, 2 with planets and planet formation, 1 with our own solar system, 3 within some stellar physics and stellar populations. That's what's in tune probably for the rest of the year. And it is my belief that in less than a year, we're all going to be saying, before Webb, we used to believe, and fill in the blank. Webb is so powerful, no one can predict what it's going to see, and more importantly, what it's going to discover. And once these images arrive this summer, we'll be going to be dazzled on how beautiful they are and what they show us and tell us about the mind-boggling universe of where we are such a small, so very small part. Our lives will never be the same. In less than a year, we'll be saying, before Webb, we used to believe. And you know, I said, started this with a Carl Sagan quote, and I'd like to end that also. Here's what Carl said. I want to back up before that. Quote, "We're all along for the ride. Every human being who's ever wondered about the majesty of the universe. Every person who feels grateful that from dust and gravity and unseen matter, everything good and beautiful and true in the world was somehow made of the stuff of stars. Webb will solve mysteries of our solar system, look beyond distant worlds, around other stars, and probe the mysterious structures and origins of our universe, as well as our place in that. The Webb time machine is going to give us some answers to questions we could have never dreamed about or even thought of. So everything we know about the universe is wrongity, wrong. And now I'm open to questions and return control back to our host,